All right, so today what we're going to be doing is working on the first sort of more complicated rule for anti-differentiation. Now, one of the things about anti-differentiation, well, two things about it, right? The reason we're so interested in antiderivatives is because of the fundamental theorem of calculus. They tell us that we can calculate these definite integrals if we just know the antiderivatives. And so finding antiderivatives is now a really big thing for us. So one of the things I want to mention here is notationally, one way that we kind of write an antiderivative is we use the integral symbol without putting any boundaries on it. So we would just write the integral of f of x dx. And this is called an indefinite integral to distinguish it from the definite integral that has bounds. And this is equal to capital F of x plus c, where capital F is an antiderivative, and this c is called a constant of integration. The reason that we do this by convention is because we want to leave open the possibility that there is some kind of a constant on here, and we also want to, get what the antiderivative is. Now, there is one thing that I do want to mention, a little caveat here. A lot of people will tell you, oh, well, f of x plus c, this is the most general form of the antiderivative. Yeah, that's almost true. It's not actually necessarily the most general form of the antiderivative. And here's why. If f1 of x and f2 of x are antiderivatives for little f of x, then f1 of x minus f2 of x is constant on each component of the domain. The problem is that some functions have a domain which has more than one component. So for example, if you think about the function 1 over x, an antiderivative for this would be the natural log of x, because you probably remember that the derivative of log x is 1 over x. Now, the thing is, the most general form of an antiderivative for 1 over x, though, it's not just log x plus a constant. It is actually going to be a piecewise defined function, which is log x plus c1 when x is less than 0, and it can be log x plus c2 when x is bigger than 0. So the reason this is possible is because, should have said log absolute value x. I was being a little bit sloppy there, but it's log absolute value x, and then we get all of this stuff. So the problem is the antiderivative of 1 over x is the log absolute value x, but we can get a different constant on each of the components because it's broken up into two different pieces here. And because of this, there's more than one constant involved. However, by convention, when we talk about indefinite integrals, we just use one constant. So the indefinite integral is the most general antiderivative on one connected component of the domain of the function. So that's why we just have one constant of integration. And the reason that we do that and we're comfortable with that is because, generally speaking, anytime that we actually need to use the antiderivatives, it's going to be when we're just dealing with a function on one component of its domain. We're usually not going to be interested in multiple components. If we do, for some reason, need to deal with multiple components, then what we have to do is we have to say, okay, we're going to go ahead and actually deal with the problem separately on each component, which we can do because we can split up integrals into different pieces of the integral, and we can put one piece in each component, so to speak. So we can break up the problem into pieces if we need to. Okay, so with that notational stuff out of the way, let me remind you about this idea of how do we reverse the chain rule so that we can get antiderivatives. Well, let me remind you what the chain rule says. The chain rule says that d by dx of f composed with g of x is f prime composed with g of x times g prime of x. So what does this mean about antiderivatives? Well, what it means about antiderivatives is that an antiderivative, if I want to take the integral of f prime composed with g of x, g prime of x, dx, this is actually equal to just f composed with g of x plus some constant of integration. Literally, I just take this rule and I reverse it. But there's a little bit of an easier way to write this out, an easier way to think about this maybe, when we're trying to find antiderivatives. And that is, let's suppose that capital F is an antiderivative for little f, then the integral of f of g of x times g prime of x dx is equal to capital F composed with g of x plus c. So the main difference here is that instead of working with f and f prime, we're working with capital F and little f now. And we can go a bit further here, actually, and we can say if u is equal to g of x, then the differential of u is g prime of x dx. And so what we've actually got here is f of u times du, and this is capital F composed with u plus a constant. So what we can really say is that if you want to try to use this procedure in practice, you're probably going to want to do something like rewrite everything in terms of a new variable u and its differential du. Remember, the differential is basically the derivative times dx. It's the derivative with respect to x times dx. If we're talking about a variable of t, then it would be the derivative with respect to t times dt, and so on. If you want to review differentials, you can go back into the earlier chapters of the Stewart textbook and take a quick look at that to make sure that you remember what's going on there. So, let's take a look at some examples of using this kind of idea in order to solve problems. And this kind of idea is called integration by substitution. And when we're dealing with indefinite integrals, it's usually fairly straightforward. So here's just a quick example of what's going on here. Let's suppose that I want to find the integral of x times e to the x squared dx. What I notice here is that the derivative of the x squared shows up multiplying the entire integrand. So I can say, let's let u be equal to x squared, then du is 2x dx. Now, I don't have a 2x dx, I just have an x and a dx, but that's okay because that just means 1/2 du is x times dx, and I can rewrite this as the integral of 1/2 e to the u du. Well, what is that going to be? We know the antiderivative of e to the u is still just e to the u, so this is 1/2 e to the u plus a constant, and if we rewrite this in terms of x's again, we get 1/2 e to the x squared plus a constant. There we go. So let me give you guys an example to try to work out here yourselves now. Let's suppose that you want to find the integral of, let's say, tan x dx. And my hint for you before you start trying to do this is think of this as the integral of sine x divided by cosine x dx. Now, see if you can think of a way to do this using substitution. Take a minute to do that, and then come back and we'll continue this problem together. Okay, so this is a little bit trickier than the example I just showed you, so if you weren't able to come up with anything, don't worry too much about it. Hopefully, what I'm about to say will make sense, but hopefully you guys were able to figure this out on your own. The idea here is I see that the entire integrand is multiplied by a sine x. And I also see that if I take cosine x and I take the derivative of it, I would get a negative sine x. So if I take the differential, I would get negative sine x dx. And that means negative du is sine x dx. So I can turn this integral into the integral of negative 1 over u du. And there we go. Now, this is something that's fairly straightforward because this is going to become negative log absolute value of u plus a constant, which is negative log absolute value cosine x plus a constant. And there's our antiderivative here. So this is a fairly useful fact, by the way, knowing the antiderivative of tangent x, but you get it by using substitution like this. And just to make sure that everybody is kind of remembering how to do these things, why don't we work through one more example here. Again, I'm going to ask you guys to pause this and work it yourself to kind of hopefully remember these kinds of techniques. Or maybe this is the first time you're sort of seeing this, in which case you may want to check out some additional examples that they've got on the books and in the supplemental things I'm going to post. But here's another example to think about. Let's suppose that you want to do the antiderivative of, let's say, what do I want to do here? Let's suppose that I want to do 3x squared sine of x cubed dx. So pause this, give it a try, and then come back. Okay, so this one was actually a little bit more similar to the first example and maybe a little bit simpler than the last problem that we did. In this case, I noticed that the derivative of x cubed multiplies everything. So if I take u and I set it equal to x cubed, then du is 3x squared dx. So this becomes the integral of, I actually literally have 3x squared dx this time. So this is literally just the integral of sine of u du. Now the antiderivative of sine is negative cosine. So this becomes negative cosine u plus a constant, which is actually negative cosine x cubed plus a constant. Remember, the derivative of sine is cosine, but the antiderivative is negative cosine. So we do get the sign flip-flopping in this case. So these are examples of using substitution in order to solve antiderivative problems. And again, if this is something it's been a while since you've seen and you're not really comfortable with it, make sure that you practice a bunch of these yourselves before we go on to the other stuff, because substitution can be a little bit tricky, especially to get used to how to do it, but it is going to be, in a lot of ways, one of our easier techniques that we see this semester, for good or for bad. And so I want to make sure that everybody's comfortable with it, because if you see a problem and you can do it by substitution, you probably should do it by substitution. It's probably the easiest way to do it. It may be the only way to do it, but usually if you have choices, it's best to do substitution. Now, in addition to using substitution to solve definite integrals, we can also use substitution to solve, in addition to using substitution to solve indefinite integrals, in other words, find antiderivatives, we can actually come up with a formula for using substitution with definite integrals. So let me explain why this is true. Let's suppose that capital F is an antiderivative for little f. And I want to do the integral from a up to b of f composed with g of x, g prime of x, dx. Well, what we know about this from the fundamental theorem of calculus is I just need to take n antiderivative and evaluate it between a and b. So that's going to be capital F composed with g of x evaluated from a up to b. But notice something here. This is actually capital F composed or evaluated at g of b minus capital F evaluated at g of a, which is actually capital F of u evaluated from g of a up to g of b. And so what this tells me I can do is it tells me, see, this is now actually the integral from g of a up to g of b of little f of u du. I've actually used the fundamental theorem of calculus in reverse here to get this answer. What does this mean? Well, it means that if I can do a substitution, I don't ever have to go back to rewriting things in terms of x's. I can actually change the bounds to be bounds that reflect u instead of reflecting x. Or more generally, I can change the bounds so that they reflect my new substitution variable instead of my original variable's bounds. So let's take a look at doing some examples of that stuff. Let us suppose that we are going to do the integral from 0 up to, let's say, pi over 2 of cosine x e to the sine x dx. So what I notice here is that the derivative of sine multiplies the entire integrand. And because of that, this suggests that I should do a substitution of u equals sine x and du equals cos x dx. And that means that this is going to be an integral of e to the u du. But what are the new bounds? Well, u of 0 is sine of 0, which is actually still just 0. U of 1, or why did I do u of 1? U of pi over 2 is sine pi over 2, which is equal to 1. And therefore, our upper bound becomes a 1 with these new variables. So this is just going to become e to the u evaluated from 0 up to 1, which becomes e to the 1 minus e to the 0, and that is just e minus 1. So this crazy looking integral here ends up just being e minus 1. And that's what it comes out to be. Now notice, I could have done this by just finding the antiderivative, rewriting it in terms of sine x, and then using the original bounds. That would have worked perfectly fine. But it would have been more work in some ways because I would have had to reconvert everything back in terms of x's. And since we don't have to do that work, why bother? It's not like we saved ourselves a tremendous amount of time, okay? It's not like the end of the world if we did it the longer way. But it's definitely more efficient to do it this way in most problems. It's more efficient to change the bounds. Another reason that you want to be able to change the bounds this way is because it turns out that for some types of problems, changing the bounds becomes really important. You're actually kind of really interested in what are those new bounds and things like this. That becomes more important in some of the applications with integration later on, where we start talking about things like reparametrizing systems and whatnot. And it's good to know how to do it, even if you decide that you would rather always reconvert things yourself. But I really do recommend that you try converting the bounds, because I do think that it is a faster method in most problems. So let me give you guys a problem here to try to work through yourselves. I know I'm giving you guys a lot to kind of think about yourselves today, but I really think this is the kind of thing that it's best to sort of practice a bit on your own and see whether you're able to do it. Let's see if you can do the following problem. So I'm just trying to think of one that will be reasonably nice here. Let's suppose that I ask you to do the integral from 1 up to 3 of 6x squared e to the x cubed dx. All right, so take a minute to try to solve this problem, and then we will come back and we will work through this together. So we're able to do it. Let's see what we get here. So as I see it, if I take u to be equal to x cubed, then du becomes 3x squared dx. And I don't have a 3x squared dx, I have a 6x squared dx, but that means that 2 du is 2 times 3, which is 6x squared dx. So this is going to become an integral of 2e to the u du. So what next? Well, the next thing that we can say is we want to change these bounds. So we're going to say u of 1, if I plug in 1 for x cubed, I get 1 cubed, which is 1. U of 3, this would be 3 cubed, which is 27. So this is going to be the integral from 1 up to 27. And those are our new bounds. Now, this is just going to become 2e to the u, evaluated between 1 and 27. So that's going to be 2 times e to the 27 minus e. That's going to be something quite large. I mean, if you want to figure out what this number is, it's something quite enormous, but that's what it comes out to be. And therefore, we are done. That is our final answer. Now, once again, I could have done this without changing the bounds and rewritten everything in terms of x's, but that would sort of add an additional step into the process that we really don't need to have, because we can change the bounds here. Keep in mind, if you are doing an indefinite integral using substitution, you do always have to go back in terms of the original variables, okay? It is only if you are doing a definite integral that you can change the bounds and not worry about rewriting things in terms of the original variables. So that is something to remember. The change of bounds and never bothering with the original variable again, that only works if we've got bounds to begin with. So it's sort of easy to remember that way. If you have bounds, you can change the bounds. But if you don't have bounds, you can't change the bounds, and you have to rewrite everything in terms of the original variables. And of course, in that case, you're actually trying to write everything in terms of the original variable anyway, because you're trying to find a function, not a number in that case, or actually a family of functions. The indefinite integral is a family of functions that differ by constants. But the point is, in indefinite integrals, you are not just trying to find a number. You are trying to find a function. Whereas with definite integrals, you're just trying to find a number, which is how we're able to avoid rewriting things in terms of the original variable. Now, how do you go about with substitution? How do you go about things like figuring out what substitution to use? Well, to some degree, it's really a matter of practice, okay? As you do the problems, you kind of get used to the sort of patterns that you see. But the general questions that you want to ask yourself are, when I'm looking for a substitution, I kind of want to ask, what multiplies the whole integrand? because my du is going to need to multiply the entire integrand. It can't just multiply part of it. And because of that, you're really looking for what multiplies the whole integrand. And when you look for that, there's really probably only going to be a few possibilities there. And those are going to be your du. So then we want to ask, does a term show up whose derivative is this thing that we got from this first step? So this thing that multiplies the whole integrand, is there a term whose derivative is that thing? Or maybe off by a constant factor. Because the thing is, all we need is to be on, we only need to hit it within a constant factor. We can always multiply and divide by constants to fix that problem, as we saw in some of these examples. So that's really what you're looking for. That's the basic principle behind how do you figure out what substitution to use. That's where you're going to be looking. Try to ask yourself, what multiplies the whole integrand, and then can we find something whose derivative is that thing? Now, generally speaking, even if you're totally lost and not quite sure what to do, there's only going to be a few possible choices for what you could do. I mean, just to give you an example, supposing that we go back to that integral of sine x over cosine x dx that I was talking about, which we did as an example. Well, let's suppose that I had been totally lost doing this. The thing is, there's really only two things that multiply through the entire integral. There's sine x dx, or there's 1 over cosine x dx. That's kind of it. Like, there's not much more I could do. I guess I could try doing something kind of funky, like take the entire thing as du, but that really isn't likely to work. So there's not a lot of choices here. And then I just have to try to figure out, is there anything whose derivative shows up as these things? Well, neither of these functions has 1 over cosine x as its derivative. So I can't get this as a differential because this is not the differential of sine x and it's not the differential of cosine x. Like, nothing shows up there. So that tells me immediately I'm probably going to want to work with sine x dx. And then I see, oh yeah, and sine x is actually the derivative of cosine x, just it's negative instead of positive, but that's okay. That's off by a constant. And so even if I didn't recognize the pattern at first, there's only a couple of different things that I could try in terms of substitution. And if neither of those worked, then that would tell me this is probably not a problem that can be done using substitutions. So if you have something and it doesn't seem like it's working with substitutions, then we probably have to go on to use some of the more complicated methods that we're going to cover later on in this course. But the nice thing about substitution, there's really only a few things that you can probably try. So try them and see what happens. But again, as you practice these problems yourselves, you will start to recognize patterns and start to see, okay, this seems like the most probable way to go about this. Like, they just kind of start popping out to you and you start to recognize, oh, I've seen something a little bit like this before, so I can probably do something similar to what I've done in the past and pick that as my substitution variable. Okay, so I'm hoping that for most of you, you guys will have seen this sort of thing, at least in our Calculus 1 course. We go up to this point. And so if, since you're in Calc 2, I'm hoping for most of you, you've seen this sort of thing before. But if you haven't, and you have more questions about this kind of thing, please feel free to let me know. And I'm going to try to also put up a little bit of some supplemental stuff that you can take a look at for extra examples and explanations and things like that. Otherwise, I will be posting some more videos next week when we really we're going to start slowing down quite a bit and going through material that you probably have not seen before. So in the meantime, hopefully everybody's been able to access everything okay, and let me know if you have any issues getting into Blackboard, getting into the WebAssign Cengage stuff, any of that kind of thing. So otherwise, I will put up a new video in a few days.